Welcome to Introduction to Additive Manufacturing, 3D Printing. This is Dr. Hamidi Sazadeh. In this lecture, we want to look at photopolymerization, another method of additive manufacturing where it uses light for the manufacturing. Another name of this process is stereolithography or SLA for short. And in this process, we use light to build 3D printed part, and the light actually induces polymerization, and the material mostly are in liquid form, in the raw material. In the vat photopolymerization, we call it vat because we have a liquid material, and the material are sitting in a tank, right? And we have a liquid photopolymer in a vat, and it is going to be selectively cured. And uh, source, the source of energy is light, and the light is going to activate the photopolymerization process. As you see in this table, we have different acronyms: SLA, which represent stereolithography. We have digital light processing, DLP, or we have digital light synthesis, which is DLS, and gel dispensing printing, GDP. And the feedstock, as you see in this table, is liquid. It works with mostly thermoset material, which is this category photopolymer. We can have, we can use metal, ceramics, composite, biomaterial. But remember, we have two blue parts, two blue circles. This means, it requires additional process. It's not, one step printing process. Mostly we know photopolymerization as a SLA, and in this process we have a light that is going to activate the material. Once the material is activated, it becomes solid. Later on in this lecture, I show you how the process works. Here we're going to look at the fundamental of the SLA. We have various components. We have a energy source, which is a laser. Okay. We may have another source, but now we are looking at the laser source. We have a scanning mirror. This one. We have this yellow line represent a laser beam, and then we have a vat which has a liquid photoresin. This one is a build platform, and this part, this is the 3D printed part, and we may have no support structures. Remember, this process also requires, for some part of it, it requires support structures. The laser beam is going to scan through and on the surface of the liquid. Okay, so the laser will hit this area. This is the surface of the liquid, and the liquid is photoresin. And once the laser hits that surface, it makes it cures the material, and this is a layer-wise process, and it's going to be repeated to fill each layer cross-section. Once each layer is done, the part is going to be indexed vertically downward. Then the next step, we have a recoater. This system, as you see here, this system spread resins to create a new layer feedstock each time. Every time this recoater has to go back and forth to provide a new layer. SLA or photopolymerization has many applications. Some of them are concept models with high details, tooling for use in short run productions, and even for end use manufacturing. Here is a small injection mold made by photopolymerization or SLA, and the material is a high performance polymer. We can use the SLA process for wearable device like running shoes. Also, it can be used for medical devices, in dental industry. SLA are widely used in architecture and product development because of high detail visualization. Another example of the SLA application is the sacrificial toolings. We talked about investment casting before, where the part is going to be sacrificed after it's coated with a ceramic shell, right? As typical investment has this um, type of process, so the part has to be sacrificed. So why we use SLA process for making the part for casting process? There are two reasons. This is actually the part that we use in investment casting. As you see, it gives you a very high surface finish relative to some other methods. The second reason is that it has a very low infill density, which is useful when the part is going to be dissolved before the molten metal is poured into the ceramic, right? This is the casting process. So the metal is going to be poured into that mold. Here we want to compare the level of details that the extrusion AM and SLA can provide. So here we have two parts, the same parts, and we want to look at their details. With SLA, as you see the bottom left, and this is extrusion. With SLA, you can generally achieve higher precision comparing with the extrusion AM, the top one, right? This is at the same scale without sacrificing speed. Why we have better precision in the SLA process? The reason is that the light sources, the light source in SLA can be precisely focused and positioned, and the material is going to be solidified in non-contact manner. Even though in the extrusion AM, the top one, the process is done with a fine layer thickness, we still have SLA in much smoother surface and sharper corner, right? As you see, the corner is sharp, sharper compared to this area, or this area. So SLA gives you better precision and a smoother surface comparing with the extrusion process. The recognized pioneer of SLA process is Charles Hall. He had the idea of stereolithography 3D printing in 1983. And he was using UV light, ultraviolet light, to harden tabletop coating material. And he found a company called 3D System, and which this company still exists today, and it is a commercialized SLA technology for rapid prototyping. And one of his other important achievement was co-creating the STL file. STL file is a file format that let him do 3D printing using his machine. And this file format is still widely used today. Whenever we want to make a model, we want to actually print a part, we have to create a model, Inventor or other CAD program, and then we have to save the file in STL format in order to define the tool path in the 3D printing software. One of the 3D printing software we mentioned last session is Ultimaker. Cura. Cura is one of the programs that Ultimaker is using for defining the toolpath. Charles Hall's first patent was granted in 1986, and the basic principle is that scanning a laser over the surface of a liquid. So this idea was to make 3D printed part by photopolymerization. So we have a laser, and laser is going to scan over a liquid over and over until the part is going to be created. There were other novel concepts in his patents, but those could not be realized uh, that time. But it showed the kind of some kind of creative idea that he had long ago. Now there are SLA machines ranging from small to large, but the process is almost the same. After each layer is scanned by the laser, you see the part index downward, and we have a blade that come and recoat the resin. And this has to be a precision process. Make sure that we have a thin and uniform spread of the resin. So your next layer is the right thickness. When the process is done, the part is lifted toward outward. So we take the part out of the resin, and if the part requires additional step process, then it will be taken to the next uh, station. And one of the really important step is support removal. And here is the question: what is the difference between SLA and extrusion AM in terms of support removal? Okay, you have that the bat, which is we mentioned before, is has contains the material, the liquid material, and your support structure and your part will be made from the same material. Okay, this is one of the important difference between extrusion AM and SLA. In extrusion AM, you can have two filaments for making the part, but now here we have one bath, one material, one liquid. So the support and the part is going to be made from the same material. Um, there are some additional steps. It's called post curing. Post curing, it means that you put the part in a UV oven, which is critical to get the final mechanical properties. So it makes the part, more rigid after the printing process. Let's look at some of the key machine elements in SLA process. First, we have material. The material is going to be liquid resin, and it will be supplied in a tank, as you see in this schematic. We have blue parts. That blue region means a liquid resin, and then we have a build platform, and the build platform is going to be submerged in a resin tank, and it moves downward. Here we have the next element, which is the recoater system or recoater mechanism, which spreads a new layer of the resin each time. Once each layer is done, so it has to recoat the resin. Another system is the laser, the scanning laser. That That system is controlled by galvanometer, which is here. This galvanometer controls, the laser direction, where the laser is going to hit on the surface. That will be controlled by this mechanism here. We have other components. Some of the new system have built-in cameras which can control the process um, in situ. So in order to make sure we have a precise part, this will be useful. Here we have laser mirror assembly from a desktop SLA printer. As you see, we have two orthogonally placed mirrors. The mirror are here, and we have a laser source coming from this way, and there are two galvanometers, as you see, this one and this one. These are two electromagnetic actuators. If you look at the galvanometer part, you see there are two electromagnetic actuators, and they can move very fast. They can move quickly, and they stop precisely, and this gives a laser scan very fast. The laser can scan up to meters per second, and also it has a good accuracy. The low-cost printer, which cost around $3,000, they use the same lasers that are used in the Blu-ray DVD players. Many of the SLA machines, they pull the part downward into the large vat of resin, right? But here we have a different design. It is called inverted SLA, and that is made by Form's lab. The Form lab came up with this idea, and another name of this machine is upside down, and it is a compact machine where you can build a relatively tall part with a shallow resin tank. Okay, and you have the system optics and the laser located down in the case here in this area. They are located on the bottom of the resin, and the part can adhere to the window, this build platform, this area, and it will move upward. Remember, that we should have a careful management of that adhesion, because that can preserve the part quality. So the laser scans the resin, and once the layer is done, the build platform moves upward one layer, so it indexes upward. And we have a orange cover, as you see, this cover that is designed to prevent the ambient light to contact that part, or the so it can protect the part from accidentally polymerizing the resin. A little more information about inverted SLA. The inverted SLA machine, the part is going to be printed upside down, and the laser is going to be directed upward. In the upright SLA printer, we have a resin tank that has to be deep. So it has to be deep enough to fit the entire part. This increases, the size of printer, right? So because you have, large resin tank, then the machine has to be, large. But in the inverted, we have a smaller resin tank, and it is more compact, and the part is going to be drawn out of the resin tank. One challenge that we have in the inverted SLA is that the build platform has to be transparent, and that allows the laser to pass through. If it is not transparent, then we cannot work with this method. Also, if we have large part, we will have some problems, because a large part requires larger force, right, to to um, keep the part attached to the build platform. So the adhesion between the build platform and the part has to be strong enough to overcome the weight of that part. So this can damage the fine features that we may have in the SLA parts. Many SLA machine um, use a scanning laser, one or more laser spot. But there is a lot of machine that use LED. LED means light emitting diodes, and they use LED in combination with the projectors instead of that scanning laser. Here is the projector, as you see in this picture. It works like a movie projector, and it has a office. Also, it is like a office projector, where you have that system which project an image of a cross section of the parts, and each time the one cross section is going to be project on the that liquid, and the image is not moving each time, so we have one image every time. Okay, and the machine has to wait for enough time, so the polymer, or the uh, whole layer is going to be polymerized. The speed between this machine and the other machine that uses a laser spot is going to be the same. So the speed is roughly the same. But this system, projector-based system, are especially useful for making small, high detail parts. The physical principle of this system and the previous one, the laser spot, is the same. And the company that makes this part, this machine is called CLIP, carbon CLIP, which is a continuous liquid interface production. Sometimes they call it DLS. And they use a oxygen inhibition, which is used to prevent adhesion between the part and the exposure window. Let's look at photopolymerization process. The underlying concept is a light activated chemical reaction. The photoresin has a photo initiator inside, right? Each photoresin has this initiator, and this is a specific molecule that reacts with the light, and it gets the polymer chain forming. So when it is exposed to light, we can have a chain of polymer. The light is going to be in the UV wavelength. It is a little smaller than we can see, and the residence time or the exposure time is extremely short. It is 1 millisecond, 1/1000 second, or even less. And in this short time, three-dimensional polymer network is going to be formed, and then we have a fairly solid three-dimensional part. Don't forget, after the process, we have to post-cure the part. Why? Because we want to have the final mechanical property. So after this part, it has to go to the next station for post-curing. The chemistry of photoresin and diversity of curing process can be adjusted in a way that it provides a wide range of mechanical properties. If the SLA process is done properly, is done well, we can have a mechanical property that is isotropic. It means the mechanical property is going to be the same in all directions. There are a lot of commercial development in the material for SLA. Includes soft material, flexible materials. We have rigid material or even durable materials. Durable material can have high temperature stability for application that require high temperature use, or even they can be used for handling fluids. In the biomedical field, the soft material is processed by SLA, as you see in this picture. It can be interfaced with body. It can be used as a scaffold for growing tissues, as you see here, this area. So they are growing tissues for the medical use. SLA can span a broader range of length scale compared to the extrusion process, because we can focus light down to very fine dimension. In fact, you can use derivatives of SLA AM to make structures with smaller than visible wavelengths. Here is one part that is very small, and it is micro scale, and this is this process is called two photon polymerization, And the same, we still have the same physical principle.
And at the large scale, we're seeing
At
variants of
the
SLA be
larger
used to
scale,
make
we can
objects
see
that
that
are taller than I am
SLA
and
can be
even much
used to
larger.
make a
And one
large
company, and at the
object.
large scale, we're seeing variants of
Here
SLA
is
be used to make
one
objects that
object
are
that was
taller
made
than I
by
am
SLA
and even
process,
much larger.
or they
And
can
one
even
company,
make
and
a
at the
larger
large scale,
part,
we're seeing
even
variants of
larger
SLA be
than
used to make
6
objects
feet.
that are taller
One
than I am
company
and even much larger.
called
And one company, and at the
Massivit
large scale, we're
3D,
seeing variants of SLA be used to
which are
make
based
objects that are
in
taller than I
Israel.
am and even
They
much
make
larger.
large
And one
format
company
printers for making a statue, or they make artifact. So they make artifact for use in amusement parks, for example. And in their process, actually, the machine dispenses the photoresin from a nozzle. Then they have a light source that follows that nozzle. Immediately, the light is gonna hit that photoresin, which provides polymerization right away. There is also growing applications of SLA to process metal and ceramics parts. Like I said before, for the extrusion AM that we use, we can make parts out of metals. Here in the SLA, we start with a composite feedstock. Here, this is a feedstock, and it contains metal or ceramic powder inside the photo resin, and then you print it to achieve a three-dimensional form, right? You have to post-process it, including a high temperature step to gives you a final dense part. So here is the printing process, then you have to debind it, then center it to make sure you have a final dense part. There is a loss, there is some loss, um, loss of the polymers. We have shrinkage during the post-processing that has to be taken into the considerations. And there are other challenges in this process, but it is increasingly used because of the complex geometry that you can make, especially in the small metal or ceramic parts.
in North Carolina.
This
First, the
video
operator
shows
takes a
the
build plate from the
industrial
stack. Note that
SLA
plate is
system
perforated.
located
He
in
loads the plate in the machine and starts the
Proto
print job
Labs
using the
in North
touchscreen.
Carolina. And the process shows how the part is completed.
The laser scans
SLA,
across the resin surface
AM.
to cure each layer. And with each layer, the build platform increments down and the recoder spreads a new layer on top. It's an ultraviolet laser and appears blue to our eyes. After all the layers are done, when printing is complete, the machine brings the platform upward, and the operator is ready with a tray to remove the platform with the parts attached. He drains the excess resin, you can see the pass-through here from station to station, where the parts are now soaked in a liquid basin. And the operator removes the parts with the support structures attached. And then he manually separates the primary support structures. Now this is a really important step because the support generation software, combined with the laser system of the machine, allow the support attachment points to be very fine and thus easy to remove. The next step is post-curing. And here a flood UV exposure is done to achieve the final mechanical properties. We see the parts inside a bright box and the parts on a turntable to even out that post-cure exposure. After post-curing, he must clean up the fine details. He removes residual support on overhangs and in hard-to-reach areas. And at last, he briefly sands the base to make sure it's flat. It begins with the operator loading the resin into the build tray of the 3D printer.
Polymer 3D printing
After the
process.
resin is loaded,
They
the
have a
machine door
special name
closes,
for it. It's called
and the build
continuous
platform,
liquid interface
upon which the part
polymerization,
will be
or
built, moves slowly down
CLIP.
to contact the resin surface. Once the build platform is in place, the printer starts printing, and the build platform moves upward as the layer-wise image of the part is projected. Importantly, this is a projector-based photopolymerization process. Each layer is projected at the same time, and the projector essentially plays a video as the build platform is synchronized and moves the part out of the resin as it's built. We see here the part is an intricate 3D lattice structure, which importantly has no internal or external support structures. After printing is complete, the build platform retracts more quickly back up to the home position, after which the operator reapproaches the machine with a carrying tray and a mat, opens the front cover of the machine, unclips the build platform, and carries the platform and the part away to the post-processing area. The first step in post-processing is washing the part, washing away the unreacted resin from the surface. This uses an automated wash station, which attaches the part and build platform and lowers those into a washing tank. Here you see on the screen the part information is communicated to the washing station, so specific parameters can be determined based on the part's design, its shape, its size, for instance. Once washing is complete, the operator removes the part from the build platform using a knife, and the part is cleanly detached and left to dry. After drying, the operator carries the part to the post-curing station. Importantly, Carbon's materials involve a two-stage cure. The shape of the part is set in the printer using light, and the mechanical properties are achieved using heat. This is a solely thermal post-curing operation that does actually the majority of the cure. Once the thermal post-cure is done, the part is complete, and we can see the operator examining it. And once again, because this part did not require any internal or external support structures, we do not see a support removal step in this video.
We have various, SLA equipment, and they can be categorized into different groups. We can look at the size of the, part, what size of the part can the machine deliver, what are the details, which is based on the size of the laser, right? The size of the laser spot. Also, the machines are categorized based on the configuration of the light source. Here we have a couple examples. Upright SLA printers are 3D System Pro 950X, and the 3D system have other models. We have inverted SLA printer, we mentioned it before, Carbon M1, Carbon M2, Formlabs, Form 2. These three, they use inverted light. We can also look at the machines from the way we expose the light. If, for example, if we use a scanning laser, these are two machines that are available in the market, Form 2 and Pro 950X. We mentioned that there are some printers that can use the light projector, for example, Carbon 3D or Envision Tech printer. They simultaneously expose one image on each layer. And then we have extrusion process in combination with the UV exposure, and the company name was Massive, which is based in the, Israel. Their system extrude the gel or the photopolymer, and then it is fully cured by the light. One of the important feature of this machine is that it can make large parts. This picture shows the machines, the SLA machines based on their build volume. Let's look at the Carbon 3D M2. Carbon 3D M2 has this build volume, which is 10,000 cc, and then we have Massive 3D, which has around 10 million cc build volume. Also, we can look at the resolution. As you see, resolution of Form 2 is very coarse compared to other machines. 3D system has the best resolution.
Projet 6000,
And
manufactured
this
by
video
3D
shows
Systems.
you
This machine
some
can
of
be
the
used
features
for
of
any type of
Projet
prototyping application.
600 SLA
It can
machine,
build in high and
which
normal
was
resolution, both
manufactured
50
by
and
3D
100
System.
micron
And
build
this
layers.
company
The
is
first thing I'm going to show you
located
is the laser
in
system
North
around the back of the machine. All right, we're looking at a laser system on the Projet 6000 SLA machine. This laser outputs UV light at 355 nanometer wavelength at about 200 milliwatts. The laser itself is generated right here in this unit right here with the cooling fans and heat sink. It moves in through some focusing optics and then back in here to a set of scanning mirrors that help direct the laser around the vat to precisely cure the UV sensitive resin. So the laser system we just showed you is on top of the machine. So the laser light will shine down from the top down to the vat of liquid resin below. This particular machine has a sensor in it that every layer it looks at the size of the laser beam to make sure the machine is operating as efficiently as possible. It uses that data to drive how fast the machine draws. Also in here we got this big silver vat is the vat of liquid resin. This particular model of machine could build parts up to 10 inches tall. This perforated tray is what the parts attach themselves to. The scaffolding and support structures grow off of this tray. Once that tray gets out of the way during the building process, this Zephyr recoating system will put down a fresh layer of material over top of the cured material, and then the laser will cure that next layer. And this process will repeat over and over again until the build is finished.
Here are some key takeaways from this lecture. Photopolymerization is a process that liquid resin is going to be transformed into a 3D solid object. And we have a chemical reaction which is initiated by a light, and it is the UV light or laser. Some of the applications of the SLA include prototyping, dental, medical devices, and we can also use it for a tooling process, tooling application. SLA has high resolution. It can deliver fine features with good, surface quality, comparing with the extrusion AM process. In the SLA, we need a support structure, and they have to be printed from single material. Therefore, it requires manual support removal. Sometimes it becomes delicate, and it can be time consuming. And also you need post curing after the printing in order to have a good mechanical properties. The next takeaway is that we can engineer the resin chemistry in a way that it gives you various mechanical properties. It can give you a very rubber type behavior, or it can give you rigid behavior. And we can have isotropic mechanical property, which is a contrast to extrusion AM process. So extrusion AM in the Z direction or build direction, the mechanical property is going to be weaker in the comparing with the other two directions. But here in SLA, we can have isotropic, mechanical property if the process is done well. Remember, the part, SLA part, can become brittle if you expose the part to, ambient light. See, one way to overcome this problem is that the part should be coated with a UV absorbing layer. The photoresin can be mixed with the metal particles or ceramic particles in a way that you can fabricate a composite part by SLA. The last point is that um, we can have ceramic SLA, so we can print polymer with the ceramic, but then later it converts to ceramic at high temperature. But this process has a lot of shrinkage that must be taken into the consideration. If you have any question about this lecture, photopolymerization, SLA process, please let me know. You can send me an email. You can post your question in the discussion in the Blackboard. Then I will, uh, write answer in Blackboard so everyone can see it. Then next lecture also is going to be about the SLA process, where we talk about the material and we talk about the physics of SLA process.